This video is on operations in binary search trees. So, binary search trees are typically associated with the following three operations. We have find, so we're finding a value and just returning yes or no. Yes, the element is in this set of data, or no, it is not. Insert, so we can add a new element into a binary search tree. And delete, deleting an element from a binary search tree. We'll talk about the first two in detail, but not the third. So let's take a look at these operations. So here's the binary search tree operation find. So to determine if a value is in the binary search tree, we repeatedly do these steps. If the value is found immediately at the root, we answer yes. Otherwise, we start the search again at the root's left child or right child, depending on the relative order of the root and the value we're searching for, the difference between the root and the target. So if the value we're searching for is less, say we were searching for the value 5, we would look at 8's left child. And if the value was 9, we'd look at 8's right child. We answer no if the root is empty. What we mean by that is if we were, say, searching for the value 12 at this point, and so we were at the point of 13, we'd gotten down that far, we would look where 12 should exist. 12 should be at 13's left child, and that root is empty. And because that root is empty, we answer no. There is no 12 in this data set. And so this is most easily implemented using recursion. We see that we are essentially doing the same steps over and over. We start here, we look at the left or right child if the value is not at 8. And then we go here again, is the value equal to 10? If not, we look at the left or right child, and so on. So we're repeating an action, and so it can be implemented using recursion. Let's first look at an example and then talk about the pseudocode for this. So for example, we could find the value 40 in this binary search tree. So we would start at the root and say, okay, is 40 equal to 50? No, it isn't. 40 is less than 50, and because 40 is less than 50, we look at 50's left child. Now, is 40 equal to 30? No, it isn't. 40 is greater than the current root, so we look at 30's right child. Is 40 equal to 40? Yes. So we return the value, yes, we found that value is in our data set. So that's what that path would look like. If we were trying to find the value 45, then we would start the same way. So we would start at 50 and say, okay, is 45 equal to the root? No, it's smaller than the root. So we go to the left child. Is 45 equal to this root? No. So we would go to the right child. Is 45 equal to this root? No. So we go to the right child. And now this root is empty. So this value is empty. Therefore, we return the value no. This 45 does not exist in this data set. So the following pseudocode implements this find operation recursively, just as we were doing. So here's our function. We can find based at a root looking for a certain target. If the root is empty, then return no, just like we would have returned at this point. If the root value is equal to the target, then we return yes, just as we did when we reached 40. If the root value is less than the target, if the root value is less than the target, we would look at its right child and do the operations above on the right child. If the root value is less than the target, otherwise, we would return and look at the right child. So this is our pseudocode for finding a value or determining that a value does not exist within a set of data. So how long does this algorithm take? Well, how many steps were there? The number of steps that there were was the height of this binary search tree. So the answer is it takes big O of h time, where h is the height of the tree. How about insert? So to insert, we first perform a binary search. So we basically do exactly what we were just doing. And then the location where the node does not appear is the location where we would place the new node. So wherever we returned a no, if we returned a no here, say we were searching for the value 16, then we would insert that value 16 at this point in the recursive code we just discussed for find. So let's look at an example. Let's say we wanted to insert 45 into this tree. So we already saw this tree does not contain the value 45. We would start at the root. We would start at 50 and say, is 50 equal to 45? No, because it's not equal to 45. We look at the left child. Is this root equal to 45? No, we'll look at its right child. Is this root equal to 45? No, we'll look at the right child. This root is empty, and therefore we insert 45 into that place value. So we would insert 45 right there. And so here's some pseudocode that implements the insert operation recursively. Assuming the value is not in the tree, you can use this pseudocode to insert a value in the proper place to maintain this having all the properties of a binary search tree, which recall, that means that at every step, all of the everything in the right subtree is greater than or equal to the root, and same at any step. So here, all the values in, for example, the left subtree must be less than or equal to this value. This algorithm also takes big O of h time, where h is the height of the tree. And we saw that that was the case. So as we're going through, the number of steps it takes is less than or equal to the height of the tree. Obviously, if you realize that something needed to be inserted higher up in the tree, it's taking really less than the height of the tree time. So the worst case is big O of h, where h is the height of the tree. Okay, let's discuss efficiency. So the operations find, insert, and delete each take big O of h time, where h is the height of the tree. So how does h relate to the number of values in the tree? In other words, the number of data values we have, which is n, the number of entries. In the worst case, h can be as large as n minus 1. So in the worst case situations, these would take big O of n time, which is not good. We're looking for big O of log base 2 time. So when would this occur? This would occur if we had a very unbalanced tree. So this is a binary search tree. It's just not a balanced one. So at each step, we see that it is true that all the values in the right subtree are greater than or equal to 10. All the values in the right subtree are greater than or equal to 20, and this could go on and on and on in the same fashion. And we could make a binary search tree of any size n minus 1 with n values that would be meeting all the criteria of a binary search tree, but not being balanced. Balanced meaning that it has sort of the same kind of structure on the right and the left. So what is the expected height of a binary search tree? We saw this one had height n minus 1. The expected height is log base 2 of n. We sort of saw a hint of that when we were looking at taking a sorted array and turning that into a binary search tree. We were taking the median at each point and putting the median values of the new halves into the left and the right and recursively doing that operation. We can make a binary search tree follow that criteria of having height log base 2 of n, where again the height is the distance from the lowest level up to the root. We can also argue that statistically speaking, even if we don't take pains to make sure that a binary search tree is balanced, the majority of binary search trees will have height log base 2 of n. There are many more balanced binary trees than there are binary trees in this sort of weird format of just one long chain of values that works in this way. So statistically speaking, even if you don't do any extra work, more binary search trees have height closer to log base 2 of n than to n minus 1. However, if that's not good enough, then we can use balancing operations from computer science to maintain the shape of the tree. So in your data structures course, you will likely look at balancing operations to make sure that your binary search tree remains balanced. So it remains having a height of log base 2 of n rather than n minus 1.